All right, let's go ahead and get started. Hopefully some more folks will show up. But let's see. So everybody here, I got abstracts from everybody here. They look good. You either had a lot of code or a lot of words. So you're halfway on either side as far as projects go. One thing I can recommend to everyone is just make sure that when you're in your projects, just focus as much as possible. Narrow what you're looking at as much as possible. So whatever your general area is, make sure you focus as much as possible into like really one kind of key issue so that you can gain, so that you can feel really confident about that key issue so that when you give a presentation you have something, you're definitely bringing some new info to the class as far as having something new to teach us about when you give your presentation. This will also help make sure that your code or your words or whatever you're writing stays focused. Let's see. You guys are both doing simulation, like kind of testing something, like measuring some sort of metric of some way. The best thing I can recommend for you guys is run as many trials as possible and collect the data, because the more trials you have, the more you can kind of look at, get enough data to look at something like an average or have a bunch of data points so that you can kind of see a trend. Just the more trials you can do running your code or whatever, the better, just so that you can really see something come out of it. So what I recommend is actually both of y'all kind of in your code kind of said something along the lines of you have like a prompt for whatever, a prompt of some sort that says, scheduling or how big a matrix or whatever you're doing in your experiment. I recommend take that out and put it on the command line. Read from the command line for whatever parameters you're getting, whether it's matrix size or algorithms. And the reason I recommend that is because you can make like a batch file where you can run a bunch of them. Like if there's a random element or like for example in the memory management thing, the random element is the fact that memory is being used while you're running it. So running a bunch of trials, you'll probably get different benchmarks each time. So putting it in some sort of batch so you can run 100 trials without typing anything and just store the results in a file and then pull that all into like Excel or something and then plot something. Here's like a sequence of if you have like a trace and you want to run it through all the different algorithms to see kind of what they spit out, you can like make a set of traces of jobs or whatever and then run all the algorithms against all of the jobs, so that you can kind of see a trend. Just anything to make it so that you're not typing anything when you run your program. That's the main thing I can recommend, is because that will make it so you can run, running 1,000 runs that you just sit your computer running for 1,000 runs and leave it. I mean, doing that kind of walk away kind of work, and you get all this data out of it, you can always make something out of that much data. You can always see something out of that much data. So, and then Niraj, I sent you some tips on how to find a good size. I don't know how much you've been running your matrices and stuff, but no, just a good way to help you find a good size by doing really big, halving it, and then doing kind of binary search, because that'll make it so that you can kind of find a really good size very quickly. It's just do something is way too big that's going to like churn your disk a lot, and then split it in half and see if it's still churning your disk, and you know whether to go to the bottom half of that. What's that? I mean, it'll just be slow. I mean, just the numbers that you get will be real high compared to the numbers will probably be real high, not in proportion to how big you made the number. So in other words, there's going to be a point where your times jump a good bit, and that means that you're really working your page file and stuff like that. So obviously any largest size matrix is going to start using page file, but you'll kind of see a jump when you start really hitting page file where a lot of the data is not fitting in memory. And then Lindsay, yours is more simulation. So yours is really just being able to get a bunch of different trials. So if you can do some sort of like, I don't know, one good thing to do would be write a quick little script or program that generates a bunch of random jobs so that you can run all those random jobs through your simulation. So you can kind of see what happens. And then if you see something with that, you can go back and look at the jobs if you notice that anything about them. Like it happened to be a bunch of small jobs, or a bunch of small jobs first and a bunch of large jobs second, or something like that. And you'll be able to see something. So, but the more trials you have in these kind of measurement types of things, the more you can kind of say, oh, that's just a fluke, or that's actually what's happening. Okay. I'm just reading for you yours is more of a demonstration, or looking at something with threading. So for yours, just really focus on something that you really want to see come out of your demonstration, so that you can focus your code. So you really make your code exhibit what you're trying to show. So if it's something like if you want to try and make the counter problem happen, like where you add from two different threads, add the same to the same number. Just really focus on that one phenomena so that you can write your code, change little pieces of it until it makes it happen, and then you can make it consistently happen, and then you can bring that in as your demonstration showing, look, we weren't lying. And it actually does make it add up differently or something like that. So, but so have you been able to look at the code? And you have some.
I was working on the program. Somehow I messed up a little bit. So I'm getting the values in error. So if it's possible, you can send me detail of program again so I can overwrite it.
Okay, yeah, I'll take a look at what might have. Okay, I'll also take a look at what's causing the errors to see if I can track down what it is. Because if it's something simple, I'll just show you that fix so that you can kind of keep going with whatever you wanted to make it do. But if not, I'll just kind of reset it back to the original Hello program. Okay. And yeah, I was just talking about the projects. Just the main thing I could recommend is just focus as narrowly as possible on one particular phenomena. Yours is also kind of yours is going to be timing some things as well, right? You want to look at the
I still couldn't find the.
I sent you a link. I sent you just yesterday. I just sent you a system call that you can use for measuring.
Because I made the coding for separate trading, and I did one like
just
whole thing put together. The only thing I need to put the timing.
Okay. Well, I sent you a link to some of the online Java documentation that you can just pop in those timer calls. So it's like a CPU clock type of system. I think it's elapsed nanos or something like that. I forgot what the call is, but it's some system call that can measure. You can also do it with date and time, which will measure the
date and time. I look at that code.
It goes to
the
milliseconds.
Way I want, it doesn't really.
No, but I mean, it should be able to measure down to milliseconds how long something takes. So the only difference is that this call that I sent you a link to is more of like how long it's running, or as opposed to the date system call, which is what's usually called wall clock time, which is looking at real actual time as opposed to time in the context of what's running on a program. No, both of them can give you a difference. There's just a slight difference between what you're measuring. One of them is how long something takes to run, and the other is how much real-world time has elapsed since you've started the measurement. They're slightly different just based on how it measures the runtime. So you can take a look at both. I'd still, you might want to put in both so that you can see the difference between this elapsed time and real-world elapsed time, which is an interesting piece of data to come out of that. But again, like a tip kind of specifically for yours, really focus on measuring that context switching stuff that you're interested in, so that you don't get distracted with a lot of other things that happen with threads and whatnot.
Actually, in that case, I had a question. When I did two trade, one I wanted to count even numbers and print it, and one is like odd numbers to print it. So I thought probably it's going to be synchronized, like one going to go first, do the even, and then the other trade going to print the odd number. So it's going to be like 1 to 3 until 100 is like a sequential, exact sequential.
I
But
wouldn't
it didn't
try to
work that
synchronize
way,
it.
because and every time I run the program,
You'd get a bunch of
different,
odd, a bunch of
but-
even.
You're right. It just
That's fine.
wasn't-
I'd do that instead.
Oh, okay.
Because synchronizing is gonna make it no. But if you were to synchronize it, you'd be going back to like really whatever you're doing sequentially. Like if you were to just count from 1 to 10, counting from 1 to 10 is easy. Counting the odds from 1 to 10 and the evens from 1 to 10 and synchronizing them so that they go in order is hard. And it's almost hard to the point that you wouldn't do that. You know what I'm saying? You wouldn't. If it's so synchronized, you don't get much benefit from multi-threading.
The second part is like one time probably I run and first thread probably pick 3 numbers, and the second thread probably pick like 10, 12 numbers.
Yeah.
Again, the first one goes like probably 5, 6 numbers or more.
Right.
But when I run the second time,
It's different.
it's probably different. So is it okay?
That's perfect. That's awesome. I mean, that's really showing threading. You see what I'm saying? Because it's not you that's coordinating all that. It's the scheduler. The scheduler's doing that, and the threading model is doing that. So that's doing exactly what you want it to do. It not being the same every time you run is good. I mean, do you see why it's good though? I mean, it's good because it's showing them trying to run at the same time. You have a single CPU. I don't know what your machine you're running. If you have a single CPU, you obviously can't run them at the same time, because you have one CPU. But the fact that the thread scheduler is handling all that, you're illustrating that by running that way, by seeing that it's this first time I ran, I got 6 numbers from thread 0, and I got 10 numbers from thread 1. But the next time I ran it, I got 20 numbers from thread 0 and 5 numbers from thread 1. You're showing that there's no tricks involved. You're just letting the threads run and seeing what happens, which is good. So then when you get your timings, you'll have a bunch of different timings, which is going to be interesting as well. Okay? But I was recommending to the other people that are doing kind of a measuring some sort of metric, some sort of, like for you, it's the time it takes to complete these threads. Run as many trials as you can. In other words, run as many times as you can so you get an average. Okay, because it will be more interesting if you can show us a lot of different runs and show us the data and the averages, as opposed to running 3 runs and then all kinds of speculation as, well, this might have happened. Well, these measurements might be completely different because of some various phenomenon, right? But when you have tons of data where you can see real averages, then you can kind of say this is the average, and you don't really have to explain everything away. You don't have to sit there and say, well, this one might be because something else was running in the background or whatever, or the more work trials you run. So the main thing, again, what I recommended is try not to have anything where you interact with it, where you have to type in stuff, where you have to type in, go from 0 to 1,000 or something. You want to put it into like a command line or something like that, where you just run it, and then you can say, okay, I'm going to make a batch file that makes it run 100 times, 1,000 times, and then just collect the measurements. So for you, that'll be a bunch of timings. So you'd have it spit out the timings, you capture those to a file, then you can import those into Excel and then make plots or whatever. Okay. So if any of you need any help with doing the data analysis or anything like that, I can give you some tips as far as how to make things, so that you can graphs impress people. So how to make good graphs to show things about what you're measuring. Okay?
Can I just do one thing on that? Just I remember.
Yeah.
Can you give me a small code? So whatever the time is on my program going to be, it just transferred to a file.
You write them. And it doesn't have to be, I mean, you don't have to even do file routines. You can just print it to the console and then just capture whatever's on the console. So, I don't know, all of you should be familiar with redirection, doing like the greater than and then redirecting into a file. So, typically that's what you want. You don't want to write a bunch of file handling routines and stuff like that. I mean, it's a pain. So, I mean, just redirect into a file or whatever, and then you can just have all the files there, and then you just pull them all into whatever you want to analyze them. That's the easiest thing to do. It's just system out, print line, and then capture. But I can give you some tips on that. But I'm not going to give you any code on that. Yeah.
As far as what's due when, I know that we're supposed to turn in a presentation by Tuesday.
Yeah.
But did you? I'm like.
The rest is just by the finals,
Okay.
The final day. That next is it? Yeah, the next Tuesday when the final is.
Right.
Just have it for me by then. Okay, so that I can grade the finals and that for submitting grades at the end of the week.
This Tuesday we're gonna stand up there and talk about it.
Yes, you're gonna give your presentations. They're not gonna be long. I mean, they're just gonna be like, I don't know, 10 minutes or so. I mean, not very long. Okay, so the main thing is and I've given some some posts on the messages as well as the same kind of recommendation that I give for writing your report, and that is just introduce the concept, what you did, your data, and then kind of some thoughts, your conclusions on what does it all mean. So something along those lines. It'll basically be like going through whatever you're going to write for your paper. So your paper is going to have those sections. You just make a slide or two for each of those sections. You're done. Right? Slides are about a minute per slide, unless you're long-winded like me. But if you figure about a minute per slide, if you make about 7 to 10 slides, 7 to 15 slides, something around there, depending on what's on the slide, right? If you have a graph on there, you could probably spend 5 minutes talking about the graph, saying, look at all these dots and look at all these, this data that I got. Yes, you have to have something. Okay, if you are comfortable enough with the topic that you can freestyle it on the board, you're welcome to do that. But I don't know. I don't know what your background is in public speaking or in threading. I highly recommend having slides, because if you try to do it on the fly, you're going to miss tons of stuff that you should have went over. And
the
you're,
abstract studied over. Have you looked at
what's that?
I already did that pre-project.
Yeah, the abstract. Yeah, I looked at it and I sent back some comments on that. So and yours look good. I mean, yours had a good kind of outline of what you're doing and what you're going to focus on. And then it sounds like you've also been working on the code, so you're well on your way to what you're supposed to be doing. Okay, but as structured a presentation as you can, especially if you're not used to giving presentations on these topics, do it like the presentations in class. There's a little bit of introduction, some pretty figures and graphs, and maybe a formula or something like that, and then some conclusions, some saying, here's why this is important, or my measurements show that, hey, look at what happens with threads in Java, or what happens with scheduling, or communication between threads. So there's something that can come out of there. But I mean, that alone is already you're already done with 5 minutes right there, just doing one of each of those slides. But
I never did it.
huh?
I never did the slide before. Never made a slide before. That's why.
Well, I mean, if you want to bring in, poster board with your bullets on it, you're welcome to do it however you want. If you want to, you bring in a sculpture, an interpretive dance, it doesn't matter. Just something that's, that kind of.
Demonstrate.
The main thing that slides and all these different aids do is they're for you to make sure you cover the main points that you want to share with the class. Okay? And I will also share another thing with you, and that is that I will have a test question on the final, probably one for everyone's presentation. Okay? So everyone's presentation will have a question associated with it that will be on the test. The good news is that that's like a free question on the test for you, right? Because hopefully you'll be able to get the question I ask about your presentation correct. Okay? On the flip side of that, that means you need to be here at every presentation and you need to pay attention at every presentation, because if you don't, unless you know a lot, and it's probably not going to be something general like that you know from theory. It's going to be about the project. As far as, I'm not going to say, recall what, this student said on this slide. I'm not going to say something like that. But what I'm going to say is, if you remember this presentation, the experiment was this, what did he find out, or something like that. And when I do these presentations, I'll usually give comments at the end. And the comments at the end, if you listen to my comments at the end, you'll know what I find interesting about that presentation. So you should also find that interesting about that presentation, because I'm going to ask something about it. Okay? Now, there's one other incentive with that, and that is, if you don't give me a compelling question to ask regarding your project, I'm going to make one up. And as you've seen with my tests, I can make up some fairly difficult questions. So if you don't come here with a very strong point that you want to teach the class about whatever it is you're doing your project on, if you don't know what that point is, then I'm going to find the point and I'm going to ask a question on it. But if you bring me the point and say, look, here's what's interesting about what I studied, about what I did my individual project on, and this is why it's important, then I'm going to say, you know what, that is why it's important. I'm going to say, I'm going to ask about that. See if everybody heard you say that this is important. Okay? So that's kind of the motivation behind the project. Motivation behind the project is to explore a topic on your own, and not only that, but also share that topic with the class so that we don't all have to go do that experiment too, right? If you do something on measuring threading times in Java, great. I'll sit here and listen to the presentation, learn what you learned from it, and I don't have to go write a bunch of code that makes a bunch of Java threads and stuff like that, because I saw what you did. I believe the the things I believe you're telling the truth, and your logic's sound. So conclusion's good. I learned something about that topic. Okay? So that's kind of what the whole thing is going for there. All right. So, and like I said before, we're going to mix those presentation days. Those presentation days are next week. Okay? We're going to mix the presentation days. We're probably going to do a few presentations the first day. Then I'm going to talk about the final. I'm going to talk about the final and what's going to be on it, a little bit of review on some of the topics. The next day, give the last couple presentations, talk more about the final probably in the most detail on that day, so you'll be ready. Any questions about the projects and everything that you have, we can address them for the whole class that day, that kind of thing. So those last 2 days are going to be presentations, which are only going to be, they're fairly short, so that'll probably leave us with plenty of time at the end to review for the final, find out what's going to be on the final, answer any questions about the final or the projects. Okay? But I do have to emphasize your slides, the slides that you're going to use. I prefer the exact slides you're going to use, because I'll be able to check them over, give you any feedback that I think would make the slides better, send them back to you so that you can make the revisions and kind of be ready for when your presentation is. But so if you get them to me earlier, I can give you feedback. But otherwise, I'm going to get them, give you feedback, probably change them so that you'll have them with the changes in them for that day. But you want to be ready to present that day, okay? But I have to emphasize that, the slides, I do want everyone's submitted to me on Tuesday, okay? The homework and stuff, I don't mind that much, but the slides specifically, I really need those to be on Tuesday, just because that's the only way to make the presentations where we're going on different days fair, and it's just I know that you can do a lot in one day. It's like that is really not fair to everyone else doing their presentation. So that's the main thing I want to emphasize, that Tuesday I need the slides in. Okay. I recommend before Tuesday, mainly because I'll tell you exactly how to change them when I send them back if you give them to me before Tuesday. But Tuesday at the very least, I'm going to randomize, probably just pick it out of a hat or a digital hat. I'll pick a few people to go the first day and then the rest on the next day. Okay? So, Um, 22 is another case study on a specific operating system, Windows XP. Before we saw Linux, right? This material, first of all, kind of relates back to all the things we've done. You notice that when we talked about Linux, we talked about a lot of concepts that we covered, even before the midterm. We kind of saw how they fit together and how they're used and how they get away from these general ideas of memory management, scheduling, and get to specifics of how a particular operating system performs that job on a system. Okay, and that's what I'm interested in them for. Mainly that they tell us the practical application of these kind of theoretical concepts that we've been going over. Okay, so also in terms of how this will be covered on the test, I'm probably just going to ask a couple questions regarding these two operating systems we saw. So kind of Linux does it this way, Windows does it this way, tell me something about it, type of thing. Okay. So right now I'm leaning towards memory management and scheduling, just because those are the ones where we see a lot of detail on the two. Okay. Like in the Linux chapter, you remember we looked at scheduling again. It was actually a second time looking at it from, because we saw it briefly in the general scheduling chapter that we saw before. But this idea of the two queues, that kind of exchange, everyone goes and gets into the inactive queue, and then you take the inactive queue, bring it over, and then now it's the active queue. So that whole idea of scheduling, we'll see that it's different in Windows, and they do a different scheme in Windows. So that's interesting to me, right? Seeing two different operating systems, the same job, right? Scheduling processes, and they do them in completely different ways, and both have both are very useful operating systems. Okay. So Windows XP, we're going to take a look at some of the overall design, and then again some of these specific implementations of the theoretical concepts we saw in the class. Okay. Not really going to, these two bullets here, we're not going to spend a lot of time on because we didn't really delve deeply into those in the theoretical chapters. Okay, we don't cover a lot of networking in here. It is an integral part of operating systems, but networking is a large enough topic that you can go take networking and learn about network more substantially, because it's a very important part of an operating system that really warrants its own kind of focus. Okay, even specialization if you're looking at various parts of computer science and information technology. Okay, file systems we didn't really cover in the theoretical sense either. We just don't. Other stuff's more theoretically interesting. File systems, I don't know, you'd probably see something more along the lines of the concepts of file systems in data structures, as well as in like databases and things like that. So, I don't know. File systems aren't that interesting to me. Okay, so we'll take a look mainly at the other things, which is the architecture of Windows XP, and some of the things like scheduling and memory management. Okay, Windows XP, it's a 32-bit preemptive multitasking operating system. Okay, and today it is for Intel-compatible microprocessors. That's not true of earlier versions of Windows NT, which were ported to other architectures, mainly Alpha. They ran on Alpha, and they also ran on MIPS, I believe, at one time as well. So they haven't always just been Intel. And these days, there are actually other versions of Windows XP. There is a 64-bit version of Windows XP, and it's actually not the flagship soon, because Vista just came out. Ornery old Vista. But it is the kind of main Windows operating system at the moment. Okay. Goals for the system: portability. Well, we have this list here. Portability is interesting in that today they actually, like I said, they do not. They have not really ported Windows XP to multiple operating systems, but a lot of, I don't know, just from nothing scientific, but as far as like the word on the street is that portability kind of leads to very clean design in operating systems. So even if you're not going to port an operating system from one architecture to another, does everybody, just real quick, what do I mean by porting an operating system or portable operating system or even architecture that an operating system?
Used on different systems.
Like what do you mean by different systems?
Well, different machines, I guess, with different, different processors. Well, in this case, it's just Intel processors, but they have different versions of Intel processors.
Right.
Obviously.
But even beyond the different versions of Intel processors, moving into completely different processors, portability is making it so that you can make code, so you can create code that doesn't run on different architectures, but that you could compile for either architecture without changing the code. Okay, that's one of the big breakthroughs of higher level languages like C, okay, and C++ and all these languages that aren't writing machine code, right? When I write a C program, how does a C program eventually get run? How can I? Is a C program something that a CPU can understand? No. So how do I get it to run on a CPU? What's that? Assembly. So how do I get it from C to assembly? No, compiler first. The assembler is actually for turning the assembly macro language into machine code, which is really a small jump from what assembly looks like to the actual ones and zeros of machine language. Okay? But the compiler takes a high-level language like C and has a standard way of transforming these into the assembler or directly into the machine code of the target architecture, okay, or the target processor. So the idea here of being portable is that I could take Windows XP, which is nothing but a whole bunch of source code, right? Mainly C and C++ source code. Okay, so I can take all of Windows XP. I can take my compiler for the Intel architecture, compile Windows XP, run that on an Intel computer as the operating system. Okay, then if it's portable, I can take the same C and C++ code. Okay, probably some minor changes for some lower level things, but for the most part, I can take the whole operating system, compile it with something for, say, a PowerPC. Okay, I can compile it and then run Windows XP on the PowerPC. Okay, that's the idea behind portability. Okay, is that you can run it on multiple architectures. So again, today Windows XP only really runs on Intel, but even interesting enough, even just on Intel, moving to 64-bit Intel is essentially writing for a new chip. Okay, there's new instructions. You have different registers, different sized registers, all kinds of different stuff, right? So it being portable makes it so that even within the same kind of family of chips, you can port it. And I'm going to compile it for that other architecture. Okay? So it leads to a clean design. Okay? Because you have everything abstract so that you can concentrate on making sure all the logic's right and everything like that. Okay? And then you usually have little tweaks or little changes that you can do to make sure that you're still getting performance, because that's usually the trade-off, right? Is if you're something more abstract or high level, chances are it's not as specific to what you're doing, so you might lose some performance. So the idea is to get a balance between them. Okay. Other goals for the system: security. Windows XP and the Windows family of operating systems actually, they get a bad rap in a lot of ways for being insecure, especially in network environments. But the fundamental plumbing of Windows XP and of these Microsoft operating systems is relatively sound. I mean, it's a very good architecture. It's just a matter of most insecurity in these in most of these Microsoft Windows environments is usually due to a bunch of additional software that's not just the plumbing. Okay, things like your web browsers, your email clients, even things that are in the core operating system configured in ways that are lenient. Okay, usually in the name of convenience, making things easier for people. So, but security is one of the kind of design goals. POSIX compliance. Does anyone remember what this acronym is regards to? Not what it stands for, because I don't really remember what it stands for. It's Unix related. Have we seen anything else that's POSIX compliant? There are portable threads. Linux is also attempts to be POSIX compliant. Okay. The idea is that most Unix was kind of Unix is different. There's not just Unix. There's Sun Microsystems Unix. There's IBM's Unix. There's Hewlett Packard's Unix. Just different companies that have Unix. Okay. There's different kinds of Unix. POSIX was meant to be a standard that everyone could write programs to, so that no matter which one I'm on, I can compile it and it'll run on that system. Okay. Windows NT, or whenever I say Windows XP and its lineage, right, and all the operating systems that it's derived from, I would also want it to be POSIX compliant, so that those same programs could also be compiled and run on Windows. Okay, but we don't typically see quite as many POSIX applications that run on Windows as we do native Windows applications. Okay, multiprocessor support. Okay, again, I'll say it again. We've seen throughout our studies of scheduling and memory and all of these different things that multiprocessing and multiple processors adds a new some complexity that's different than the issues faced with single processor systems. Okay, everything that we've seen from scheduling to locking, right, all these different things have different issues when you get into multiple processors. So designed from the ground up to be multiprocessor capable. Extensibility, probably one of the very strong aspects of Windows XP is the fact that it is very extendable, especially in the sense of drivers for different pieces of hardware, right? The code that interfaces between the operating system and hardware. So very extendable. International support, that's more application stuff. And then backwards compatibility with older Windows systems. Okay, some think this is some thinks this is a bad thing about Windows. Okay, is all the backwards compatibility. Those people are usually technical people, right, like computer scientists and things like that, because adding backwards compatibility, what's the trade-off of that? Okay, if I am a new operating system, Windows XP, okay, or I'm Windows NT, or any in the lineage, Okay. What is the trade-off of making sure I can run DOS programs?
It won't have all of like most of the new features that are in the XP stuff, like security features.
Right. What do you mean we won't have that?
What we built, like MS-DOS doesn't have like
Right.
say, you know, security that XP has.
Right. So, well, yeah. So on one hand, we definitely won't let MS-DOS definitely won't be able to gain all of the features of Windows XP. Okay. But is there a drawback to adding it to Windows XP? That's kind of a drawback for the MS-DOS programs, but they didn't have that to begin with, so they can't really be missing those features that they can't do. Was there a drawback in having it in the operating system? It's backwards compatibility.
Word.
Huh?
Take off more words.
Yeah, but we don't have to write it. Microsoft took care of that for us.
Microsoft can't sell the newer version.
Well, I mean, if these other reasons are... What I'm saying is that if they left it out, right, the drawback would be we won't be able to run our old programs on it, right? But putting it in, is there a drawback, is what I'm saying. There might be. Okay. One is supporting that you have a whole additional subsystem that is running or is there on the system that's not the new stuff. That's not the, for example, if the main thing is you have to bring some of the drawbacks of those old operating systems with you when you go to a new operating system. I don't know if any of you were there during the transition from like DOS to Windows, or especially into the newer Windows, where you start getting things like, for example, long file names. Okay? If you're going to support DOS, now all of a sudden you have to make sure that you have some way of accessing these file names that didn't exist in the DOS days, right? If in the DOS days, if you could only have 8 character file names, and your new operating system has 256 character file names, something's got to happen, right? I mean, if you're going to be able to run these old DOS programs.
Why does it matter?
What's that?
The new stuff can be 256, right?
Right.
The old stuff's only 8. You're running the old and the new, all of them 8. So it doesn't matter.
What happens when a file is more than 8 characters?
It doesn't matter because the Windows can report. You're not running it in DOS. You're running it in XP. So
Right. But what I'm saying is how do you view the file system? Should there be gaps now in the file system when you're in a DOS program?
But you're not running in DOS. You're running in XP.
But we have a DOS compatibility layer. We can run DOS
But
programs.
does that mean you're running DOS?
Okay, you write a program in DOS that has, for example, enter a file name as one of the prompts. Okay, all your checking says 8 characters, right? You do checking and stuff like that. When you're in that, how do you interface with the file system? Because this file system, what happens when it feeds it a file that's greater than 8 characters? Or how do you access a file that's greater than 8 characters?
Don't you know?
Okay, so you have a tilde and then another number. So notice that now the file system has a complete layer written into it for translating between long and short file names. Okay, if we did not have an MS-DOS compatibility layer, we could have made that file system without any of that stuff in it and any of the overhead concerning that stuff. Right? So at the very least, the 8 bytes of data that you're storing on the file system to represent the short file name for that are gone. And you get it back if you don't have them. So, I mean, that's the trade-off between this kind of being compatible, backwards compatible, and having your new technology that you want to use. Okay? Uses a microkernel architecture. Anybody remember what I mentioned? Microkernel and monolithic kernel before. Anybody remember what that's regarding?
Big and small kernel.
Big and small kernels. So does the small kernel not do as much as the big kernel? Or an operating system using a small kernel, does it do as much as an operating system using a monolithic kernel? Huh? Okay. So, why have a big one?
Is that like risk and sys? Is it kind of the same thing?
You could tease an analogy out of it. Okay. What is the kernel?
It's what deals with communication hardware and
Yeah. So it's the real kind of centerpiece of the operating system, that real the core piece that's between your application type stuff, right? Your programs and everything, and then all your hardware things like the CPU and memory and things like that. Okay. So the idea behind a microkernel is make that core piece as small as possible. Okay. And then you can write things outside the kernel to handle all the things that an operating system needs, like whether it's device drivers or something like that, where you can actually communicate between this kernel and these other little pieces of software that handle things like your disk drives and your network card and stuff like that. So what would a monolithic kernel do? Into that one piece of software, right? That core piece of software that's the kernel. Okay? So what's the trade-offs? Why one over the other? Right? Because we've already stated that saying you're monolithic, right, or microkernel doesn't necessarily say that you have less features or more features or whatever. So what's the trade-off? Okay. It's kind of a trick because some would debate that there aren't a lot of trade-offs. It's just a design decision. But the idea is that microkernels keep the core kernel piece simple. It makes it so that a lot of people say smaller code is less bugs, right? If there's a small piece of code, it's very easy to look through it and say, oh, are there bugs? If you have a large piece of code, the interactions and stuff make it harder to look through. Some people say that one's faster than the other, right? If you're a microkernel, chances are you have to do some sort of messaging between the kernel and other parts, whereas a monolithic kernel, you can just, it's all in the same piece of code. You can just grab whatever memory you want or processes you want and stuff like that and use them, right? But that's mainly more concerned with design from the standpoint of developing an operating system. Okay, if you're actually coding the operating system. Okay, but Windows XP is microkernel, and a lot of the modern operating systems are not.
So what's an example of something that would be a monolithic but not in a microkernel?
And I'm not 100% sure if Windows XP does this, but like a network card driver. Okay.
Drivers.
Yeah. So like one approach is you write a network card driver as a separate piece of software, and then you have a interface, like a message passing interface between the kernel and the network card driver. So obviously the network card driver has some privilege that it can talk to the hardware. Okay. But all the real logic of that driver can be written separately, and there's a well-known interface between the two. Whereas putting it in the monolithic kernel, you can kind of you're in the same code space as the rest of the kernel, so you need a byte from it, you just grab it out of memory, and as opposed to packaging it into a nice message to send. Okay. Okay, and then there's different versions of Windows XP. Most of them share the same kind of core pieces and then have different features enabled or disabled depending on which of the features or which of the versions you get. And then there's usually a big difference in price as well between the different versions. Okay. Windows XP's lineage is from NT, which stands for New Technology. Okay. This was kind of their first entry into more, I guess, robust operating systems. Before that, they were focused on desktop graphical user interfaces like, Windows, like the original versions of Windows, Windows 3.1, and things like that, even Windows 1.0, they were all graphical user interfaces running on top of DOS. Okay. Then eventually, they started migrating towards having taking DOS out of the picture and just writing the whole operating system from the ground up. In other words, from the hardware up to the user, they wrote the whole operating system, as opposed to DOS, right, running at the core as the operating system, and then a graphical user interface on top. Okay, so in a lot of ways, NT was a successor to DOS than it was a successor to Windows. Okay. And a lot of NT was kind of born out of Microsoft was originally one of the co-developers of OS2. Anybody heard of OS2? You hadn't. It's not uncommon not to have heard of OS2. OS2 was IBM's kind of flagship desktop operating system for a very brief window, and it, for the most part, failed miserably. But it was originally being developed by both IBM and Microsoft, and then Microsoft kind of went their own way and then used most of their stuff for NT. Okay? All right. Okay, extensibility and portability. Okay, extensibility by creating all of these different layers. Again, starting the very base of it with the microkernel architecture. Okay, we have a what's called an executive, which is kind of almost the kernel, right? There's a kernel. Actually, there's a diagram here. Hold on. Okay, so you have something like a kernel here. We'll talk about that. But the executive is still kind of in the what's called protected mode. This is really it can access things like the hardware directly, as opposed to going through some well-defined interface. Everything above this dotted line is what's called user mode, and user mode needs to talk to the operating system in order to get access to any resources. Okay, so this line here is kind of saying, am I a program that just runs like any other program, or am I privileged in some way that I can interact with some of the more kind of deeper parts of both the kernel, or both the operating system and the hardware? Okay. Now there is also in Windows, in the Windows operating system, there is another layer that they put in between the hardware and the rest of this protected space, this privileged mode. Okay, and that's called the hardware abstraction layer. Okay, this is another piece related to this extensibility and portability. Is there is an additional piece of software between the kernel and the hardware, so that the kernel can mostly be written still in high-level languages that are portable, that you can just recompile for different architectures. And then there comes a point where you have to write things that know specifically about the hardware. Okay, you can only be abstract about what instructions you're going to run and how you're going to interact with devices. You can only do that to a point. Okay, there has to be a point where you actually go in there and start manipulating hardware. Okay, so what Windows attempts to do is consolidate all of this code that would be specific to any kind of CPU, computer architecture into what's called a hardware abstraction layer. Okay, and the huge benefit from this is that if you change platforms, you change architectures, you change hardware, you can change this little piece and then leave the rest actually not only portable, but also you might even be able to leave it the same binary code. So, for example, Windows XP, like if you went from a single processor to a multiprocessor, okay, both of them might use a single processor machine and a dual processor machine might both use Intel chips, let's say. Okay, they're both Intel chips, so both of them can run the same binary code, right? But they are different, right? Sending instructions to a single processor is different from sending instructions to multiple processors, right? So what you can do is just change this hardware abstraction layer, and even the kernel can remain the same code running on both platforms, right? And whenever it tries to go to the CPU, it doesn't go talk directly to the CPU, it goes through this hardware abstraction layer. So it's a very good modular design. And, it's seen throughout software engineering, this idea of modularity. Okay. This part right here is another. This second bullet is an interesting aspect of microkernel designs mainly, but also with highly extendable modular operating systems. Is many of this the really important subsystems are run in user mode. Okay, and what I mean by user mode is going above that dotted line. Okay, so things like some of the POSIX piece for Unix type applications, these subsystems that let us run this backwards compatibility types of software, like running old MS-DOS programs or old Windows programs, OS/2 programs, services like security and authentication. Notice all of these are running above this dotted line. Okay, they're all running above this user mode dotted line, which means that none of these programs or subsystems are privileged in that they can't directly talk to the kernel or can't directly talk to the hardware and whatnot, right? So what they do is they actually interact with the kernel and all these different pieces like the executive. They interact with them just like any other program to do their job. Okay? This is different from something like a monolithic kernel or something that's not quite as modular, where anything that has to do with the operating system you kind of put into this privileged mode. Okay? And doing that, okay, makes it, first of all, very extendable. Because if you have, for example, you want to be able to run older, a different type of compatibility like DOS or old Windows programs. If you have another thing that you want to be compatible with, you can just pop in another one, right? Just like you throw in as many of these as you want. It's very modular. Okay? The other thing that's very good about this concept is that none of these subsystems, none of these additional components that are running in user mode can harm the system for other subsystems. So what I mean by that is, let's say you're running an old DOS program, right? If you run an old DOS program on a Windows XP system, you can't run it directly in Windows XP. It's a different operating system, okay? But you can run it in this piece that is an MS-DOS compatibility subsystem, okay? So you have an old DOS program, and it does whatever it does, okay? But it does computations, it uses resources like the CPU, memory, all of these things, okay? If this program is badly written and it corrupts memory or does something wrong with the CPU or doesn't want to yield the CPU or anything that it could possibly do wrong, okay? Let's say it crashes and leaks all its memory. In other words, it doesn't free all its memory. Well, it being in this user mode, it can't do anything to any of the resources because all of its resource utilization was mediated by the subsystem in user mode. So if it crashes, that's fine. As far as the operating system is concerned, it's just another program. If it crashes, I'll take all the resources it was using and free them up or give them to somebody else. Okay? This is very interesting in that the same DOS program crashing on DOS, right, where DOS is this piece underneath the dotted line, right, that same program crashing could render the whole system unusable. Okay? So what this design does is it actually makes Windows XP a more stable DOS than DOS was. Okay, in the fact that it separates all the DOS programs into their own little subsystems, and whatever they do that might have previously rendered the system inoperable is protected from everything else. Okay, that's a very powerful aspect of this design. Okay. Take a break. Okay. Take about 5 minutes.
So, for my project, you're more interested in presenting the data and how it was processed and what came out, right? Rather than
Here's the
here's how this
program.
is, right?
Yeah. But I mean, some discussion of like what the some talking about the program itself, like your simulation,
Right.
gives people confidence in what they're seeing with the data. So saying something like, I simulated it by doing this, but as far as like how the program worked or anything like that, that's not important. It's really the model I kind of used was this, and then we can all kind of look at that and go, that makes sense. That seems like a valid way to look at scheduling. And then you can say, okay, and then by that, then here's all the data that came out, and I think the data says this. Then we can all sit there and debate about whether or not the data says that. And then we can question your validity as a scientist. at that point. But yeah, wow them with data. That's how you do it. My thousands of data points can't be denied. Then anything everybody else says, conjecture, pure conjecture. I have empirical evidence. And then you can flip over the table and storm out. nonsense. All of this is nonsense.
Think about writing a song.
Oh.
Singing,
Like maybe bring a
My
guitar,
presentation
like a
song.
yeah. You should bring like a nice acoustic guitar. You know, prop up the one foot. You know.
That'd be much more interesting.
You know, I'll listen to a presentation about scheduling done to, you know, folk music.
Don't say that.
You're welcome to do it, but I critique, you know, data given to me through folk music the same as I do anything else.
Miss a chord.
You know, but I'll even add additional things to critique, like, you know your rhythm, your
Pretty variable.
yeah. So you're just adding another layer of complexity that could be criticized. It's like, first of all, I think your model is flawed in that I don't think it takes into account this. Second of all, I mean, your performance was maybe if you were on beat, I'd buy that your model like worked, but come on. Plus, I don't like folk music, so that'll automatically put me in a bad mood. When I'm in a bad mood, I find a lot more
So
flaws.
what if we bring in like cupcakes?
Cupcake stuff, and I'm like,
Memory
man,
management cupcakes.
huh?
Memory management cupcakes.
Yeah, like actually, if I
Bring my data points.
right, you could if like each of your is a gummy bear or something, you could snack on the different data points. See, I don't really like sweets though, so you're still
How
gonna.
about high graph pizza?
Oh, now we're talking. See, because then I'll be like, it's good pizza, and I'll be like happy and stuff. I'll be like, man, let's just eat pizza and we'll get through this. And look at the data. Like each data point was like a pepperoni. I'd give you a lot more wiggle room as far as interpretation goes. Pizza's good. Yeah, savory types of treats. Like cupcakes, while everyone else might like them, I'll still be sitting there. Cupcakes, I don't like cupcakes. Wrong. Your model's wrong. It's flawed. Alright, we'll talk a little bit more about. I want to get to a little bit of scheduling. And then we'll do memory management on Thursday, I think. Okay, so we saw our picture of the architecture. Has everybody got kind of a general, I mean, you don't have to have a very detailed idea, but just generally this dotted line and what it means? Idea that everything above the dotted line in this user mode is really processes and programs in the sense of what we've been seeing in operating system. Okay, the regular programs that are scheduled and managed by the lower level things that run in privileged mode. Okay, and the privileged mode is kind of outside of all these more abstract views of memory and CPU and things. This is low level. All of this stuff actually can see the hardware, can interact with the hardware, can interact with the memory of different pieces of the operating system. Okay, this is kind of all direct manipulation of the computing system, whereas this is all the part above the dotted line is all running on the computer system, but still mediated by all of our software under the dotted line. Okay, we've seen programs. We've kind of been thinking of programs run by users in this way, right? If I have two processes run by users, right? The operating system schedules them. The operating system gives them memory. The operating system, manages how they can get to files and how they can get to printers and all these things, right? That's how we've been talking about programs, right? If the operating system wants to, it can take your program, wipe it out of memory, and throw it away if it wants, right? It can take it off the CPU. It can put it on the CPU, right? It can put other processes on the CPU instead of it, right? All of the operating system is managing those programs. Well, these act like, these things above the dotted line, these subsystems, act like those kinds of programs. The only difference is that they're an integral part of the operating system. Okay? And this design is very helpful in that it compartmentalizes and isolates and mediates these different subsystems. Okay, which is very powerful. But it does add a layer in between, for example, the security subsystem. The security subsystem not running below the dotted line means that it has to go through the same mechanisms as any other program for getting to the different pieces of, the different resources of the operating system. Okay? But on the other hand, if something goes wrong with it, or you want a different security subsystem, or whatever, we have the flexibility to do that. Okay? The executive piece that's below the line is below the line, so it is in a privileged mode. It has this, this more direct access to different resources and different parts of the operating system. But it is put outside the kernel, okay, and it runs in its own. It runs as its own program, okay, but it has that kind of unlimited access that the kernel does, okay. And the reason for this is just it keeps everything separate, and again, all the good things like modular, portable, all that's extendable. Okay. So, the kernel. Okay. Never paged out of memory. Execution is never preempted. Okay. That doesn't mean that it's always running. It's just not preempted. Okay, preempted means something from outside the program comes and stops you, right? The kernel isn't preempted. The kernel gives the CPU back to whoever needs, to whatever it wants to use it. Okay, but no one's more powerful than the kernel, right? No one's going to come in and say, "Hey, kernel, I need you to get off the CPU because I need to run some other code." It doesn't work that way. The kernel says, "You know what? I'm going to let you run some code by scheduling you. And you know what? When I don't want you to run anymore, I'm going to take you off." Okay, so the kernel's the boss of all that. Okay, 4 main responsibilities: thread scheduling, interrupt and exception handling, processor synchronization, low-level synchronization, and then this recovery after a power failure is kind of thrown in there. We don't really need to talk about that. That goes into a whole subsystem that we didn't really talk about, nor is very interesting. But thread scheduling, we can imagine what that is, right? The actual scheduling that we talk about, right? When we talked about the scheduling chapter, kernel does it. Okay, all the code for all of the putting processes on the CPU, they're calling them threads, putting them on the CPU, letting them run, taking them off, deciding who's going to run next. All that's in the kernel. The kernel's in charge of that. Interrupt and exception handling. Okay, this idea that we get an interrupt, we run a little piece of code to handle an interrupt, and then return to what we were doing. Well, that little piece of code that we run to handle the interrupt, kernel does it. Okay. Low-level processor synchronization. Okay, this has to do with, they have a list here at the bottom. Things like mutex, semaphore, right? All these things listed down here. These types of primitives are provided by the kernel, and they need to be provided by the kernel, because if you want to do things like lock and make it so that multiprocessors don't clobber each other's data, right? Make things atomic, right? All of these things that we want to do, the kernel has to handle that, okay? Because it's the one that can really get down there and say, no one's allowed to interrupt. I'm going to run this, and I'm going to complete it before I let anything come back on. Or spin locking, or whatever we need to do to make it so that two different things can't run critical sections at the same time. The kernel's in charge of that. Okay. It's object-oriented, okay, which is just a way of looking at the data and methods, okay. We have a dispatcher objects, which are these different synchronization and dispatching is what they're calling scheduling and whatnot. It's related to scheduling. Okay, and then control objects, which is different kinds of like they're listing here, like interrupts and power status and asynchronous procedure calls. All of these are these different types of events that we talk about when we were saying, like, if new data comes in off the disk and we interrupt, right, or some keyboard information has been typed in and we need to get it from the hardware, mouse movement, any of these things, these will end up being seen in the kernel as control objects. Okay. Processes and threads. Okay. Threads are the unit of execution scheduled by the kernel dispatcher. Okay. So they're saying they're not really differentiating between the idea of a process and a thread. They're calling them more threads. Okay, and that's just a matter of terminology. Okay. Each thread has its own state, including a priority, processor affinity, and accounting information. Okay. The priority we're familiar with, and there are different scheduling algorithms that support priorities. States we know all about: ready, standby, waiting, all of those things. Okay. Processor affinity. Anyone want to take a stab at what that is? Huh? Right. Affinity is liking or preferring. So what do you think a thread having processor affinity is? No, because a thread can only be running on a CPU architecture.
So, for it to like one over the other, it would have to be
Multiprocessor, right? So if you have multiple processors, you can have a processor affinity, which means you'll prefer to run on one of the processors over another. Normally, the kind of the default view of multiple processors is treat them all the same. If I have 4 processors, I can run on any of the 4. Processor affinity can make it so that you can prefer one over the other, so that this process always runs on processor 0, or this process always runs on processor 1. So it kind of starts tending towards what kind of multiprocessing. We normally see is what's called SMP. What does SMP stand for?
Small.
Nope. Symmetric. Symmetric multiprocessing. So what do you think the other type is? Asymmetric, right? So asymmetric multiprocessing. If you do this processor affinity where all these different processes want to run on specific CPUs, well, you're not symmetric anymore. They all kind of go to a specific CPU to run. Okay? And then these thread states, we're familiar with this when we were talking about processes before.
Does it, in a multi-processor system, are there processors that are suited for different things?
Typically, no. I mean, typical, like SMP, symmetric multiprocessing systems, is the same CPU and just it's the same model CPU in each socket. In fact, most of them require that they be the exact same CPU. When you start getting into like multi-core, it's the same chip with 2, CPU cores on it. So typically, they're all the same. There are systems that do have different processors in them, and there's also the concept of processors that aren't CPUs, like graphics cards and stuff like that. Graphics cards are actually very powerful processing units these days, so you can kind of see that as kind of an asymmetric CPU type thing. But typically, when you're talking about multiprocessor systems, it's the same processors.
So why would a thread prefer one processor over the other?
One thing you can do is keep, just as far as scheduling and overheads and things like that, keeping them on one, you can gain benefits like cache coherency, right? If you're always running on the same one, there's a greater chance that the data you want from cache is still there.
So it's not so much it's picking one that's suitable for it, it's just
picking one and sticking with it. Yeah, just having that affinity for one, just preferring one, but not for any reason of which one it is. Now, and there's also the idea that if you have 2 things that have affinity for different processors, well, they're going to tend not to clash. They're going to tend to run around the same time, right? Because if you have a choice of where to run them, you just spread them out. But one's always going to be running over here, and one's always going to be running over here on processor 1 and processor 2. Well, even if one's idle, you still can't go use that CPU because you're preferring this one. So there's different things that will happen. It's typically for very, very detailed like performance management of a system, whereas the general rule is just treat them all the same. Now, that being said, there are multiprocessor types of systems that can have different CPUs, especially ones that are very expandable. Like computer science department has a older multiprocessor what was it? SGI box, SGI, which have a system called our system's named Hydra. It has I think 24 CPUs or 32 CPUs, and some of them are older than the others. So some of the processors are actually slower than some of the others. They don't have to. I mean, typical. Like I said, the typical setup is that they're all the same.
If I get the multi-processor one where I have two random processors and then run the same architecture.
No. If your system's not designed to handle, these aren't go to Fry's and get or Best Buy and get these are SGI workstations that have like card slots that you can pop in a bunch of different CPUs. So Hydra actually was a pretty big box back in its day, but it's really old now. But I don't really know of any Intel architectures that have, I don't know, I'm sure some of their supercomputer stuff does, but your typical motherboards and stuff won't support asymmetric multiprocessing. Okay, just real quickly introducing the scheduling. We have different priority levels. XP has 32 priorities. We saw before, Linux uses its own priority system. I forgot how many priorities there were. I think there were 100, but I think it was 128. I don't know. But anyway, these are just numbers which tell the scheduler how to balance them in regards to how long a time slice to give them, right, a quantum, and then how often to schedule them, okay? And we had this whole idea of changing the behavior, changing the size of the time slice, changing the, how often you service a particular group will change their performance, right? CPU-bound jobs, we like to run for long periods of time, not very often, right? I/O-bound jobs, we want to service as often as possible because they're going to give up the CPU, and then we can, they won't hog the CPU because they'll yield it when they're waiting for I/O, okay? So, characteristics of XP's priority strategy tends to give very good response times to interactive threads that are using the mouse and Windows, okay? What does that mean? It means we are going to service these interactive threads very often for small amounts of time. Okay, because we know that we will not get tied up with the CPU because we have to wait for usually a human being to do things like move around or read a screen or something like that. Okay, so what are they saying is that if your process is accessing the mouse and accessing the graphics to make these windows, so to draw these windows and move them around, right? They're making the system calls which draw the windows and whatnot. Okay, you're going to start getting prioritized higher, which means I'm going to give you small time slices, service you often. If you're not using these things, you're going to be considered more CPU bound. So what ends up happening is I'm not going to service you as often, but when I do, I'm going to give you a large time slice so that I don't interrupt you, you don't get all this overhead from context switching all the time. Whereas these I/O bound jobs don't care about context switches because they're usually just waiting. Okay? So, scheduling can occur when a thread enters the ready or wait state, when a thread terminates, or when an application changes a thread's priority or processor affinity. Okay? What does that mean? These are the points at which the kernel scheduler can make decisions as to whether or not it should put you on the CPU. Okay? Entering a ready state, when does this often happen? Entering a ready state. Anybody remember? Okay, so if you get yanked off the CPU and put into the and taken off the running state, we'll put you immediately into ready because we know you're ready to run because we interrupted you while you were running. Okay, how else do we often get to ready state? After you get done starting, the next place you go is ready state, saying you're ready to start running instructions after all the loading and whatnot goes on. Or if you were waiting for something like I/O and your I/O gets done, you're now ready. So you can move over to ready and be scheduled. Okay. They're saying you can also be scheduled during a wait state, which is usually, if you go into the wait state, the scheduling that's going to occur is you're off the CPU, right? As opposed to when you're in the ready state, your tendency is to want to get on the CPU. Okay. When a thread terminates, okay, again, that's a time to take you off the CPU. If you're done running, there's no need to be scheduling you for CPU time. When an application changes a thread's priority, okay, so if these priority levels get changed, that's obviously a good time to reevaluate and decide whether or not you should run, right? Because if your priority has changed, how you get scheduled and things are going to change with it. Or processor affinity gets changed, which means you now, like let's say some process or a user changes your processor affinity. Well, at that point, you should be rescheduled because you may be running on the wrong processor, or you need to evaluate whether you can run on your preferred processor. Okay. Real-time threads are given preferential access, okay, but are not guaranteed that they'll execute within a particular time limit. Okay. This term soft real-time comes up. We didn't really talk a lot about real-time in general. You know, I kind of alluded to it when we were talking about Linux and some of the other scheduling discussions. Real-time is about being able to schedule things reliably within a particular amount of time with a particular amount of waiting. Okay? And hard real-time is being able to guarantee those things. Soft real-time is trying to do those things. Okay? Most of your more general purpose operating systems like Windows XP, most versions of Linux are soft real-time or no real-time at all. Okay? But soft real-time in that if they can't do it, they won't terminate the process, they won't error out or anything like that, and they can't make guarantees. Okay? But usually hard real-time as opposed to soft real-time is done with a specialized operating system. Okay? I believe that, I don't know if embedded XP, there's other versions of XP like embedded XP, that may support actual hard real-time. There are hard real-time versions of Linux, and then there are also more specialized operating systems that support hard real-time. Okay? Hard real-time is typically seen in embedded systems, sensor readings, you know, stuff that interacts with the real world. Okay? Like, you would hope that your car's computer is running a hard real-time operating system. Okay? Because there is no, you know, I'll schedule you as best I can when deploying your airbag or something like that, right? If you're going to deploy the airbag, you either deploy it or you don't. There's no, you know, deploying it half a second later because that's when you got around to it, right? So the good part is that chances are the airbag will deploy. The bad part is that if it can't deploy it, it can't. It can guarantee that it can't. It won't deploy. Okay, so we will continue a little bit more with the scheduling and then also take a look at the memory management on Thursday. And then we'll be done with what we want to look at with XP. Okay? And don't forget there is an assignment that's due on Thursday. Yeah, the security and protection.
I was looking for your